Okay, so in this video, we're going to be talking about the idea that was introduced in CSE 143 of binary trees and binary search trees. So this should hopefully be at least a little bit familiar, but we want to make sure we're really solid on some of the terms we're going to use and definitions that we'll use for these problems so that we can kind of tackle some of the more advanced applications of them. So as a reminder, a binary tree is a collection of nodes where each node has at most one parent and anywhere from 0 to 2 children. We think of these structures a lot like linked lists, but now there's like an extra field you can have to have a left child and a right child. Now, there's usually, with these tree terminologies, there's usually lots of kind of terms that come with it. So for example, you might have the root node at the top. Whoops, I'm not sure why that red one appeared too. We usually think of having a root node at the top that has no parent. It's kind of the top of the tree. Usually people call this like overall root in their Java code to represent that field. We also have the idea of leaf nodes. So leaf nodes are nodes at the bottom of the tree that don't have children. And so you can already kind of tell that this picture is a little upside down, right? Where the root of the tree is at the top and the leaves are at the bottom. But if you just like turn it upside down, it looks like a regular old tree that we're used to. We also commonly think about this idea of subtrees. So when you have a root node kind of at the top that has children, sometimes it's useful to think about, instead of thinking about all of the individual nodes that are descendants of that top level node, is just think about, whoops, wrong color. Just think about this, wrong color again. We'll get it one time, there we go. Thinking about all of these children as kind of this one child and all of the descendants underneath it as kind of just one big subtree. And it helps think about, if I don't have to worry about all the details of like what this tree looked like underneath, it's sometimes a helpful term to use was like, oh, go down to this subtree, go down to this subtree. Usually people might define trees in this very formal recursive way, where like a tree is either an empty tree, which we would represent as null, or a root node that has 2 tree children. And those tree children follow the definition of the tree, where they could either be empty or nodes with 2 tree children. It goes on and on and on to build these nice, big, beautiful trees. One other term that we're generally going to care about, especially in thinking about how to implement these trees efficiently, is this concept of the height. So the height of the tree is the number of edges contained in the longest path from the root node to any leaf node. And what we mean by that is we mean kind of how many arrows down do you have to go to get from the root node to a leaf node. And so in this context, the height of the tree is 3. Some other places define height slightly differently. Sometimes they define it in terms of the number of nodes, but we're going to define it in terms of the number of edges, the number of paths you have to go down to get from the root down to the leaf. Now that's going to actually bring up some interesting cases that I actually want us to talk through. Let's do some examples of computing the heights of some trees. Let's start with this tree on the left. The height is the number of edges contained in the longest path from the root node to any leaf node. So there are usually multiple leaf nodes in a tree, and so the height is just going to be the longest path from root to leaf. And so in this case, the one on the left, there are 2 edges you have to take to get down to that leaf node, so its height is 2. Okay, now consider this middle case where our tree is just a single node. Now, how many edges do we have to take to get from root to the leaf? Well, in this case, it's none because the root is a leaf at the same time. So we'd call this tree having height 0 because there are no edges between the roots and the leaves. Which then brings up an interesting question. Well, isn't an empty tree also a valid tree? And the answer is yes. So what happens if overall root was null? What should the height of that tree be? If we said 0 here, it'd be really confusing because that tree in the middle also has height 0. So by convention, we say it's some other value, like -1, to kind of differentiate it between the two. So usually it's really important when we're thinking about applications that use height to make sure we're talking on the same terms about what height means, and especially about some of these edge cases where it's not super well defined what the height of an empty tree should be, and by convention, we're going to use -1. Now this concept of the height of a tree is going to be very crucial when it comes to thinking about the efficiency of operations that work on tree structures. So here's an example of 2 trees that have the same height. They both have height 3, but they look very, very different. So consider the tree on the left. There's this nice, big, beautiful, bushy tree where each node has 2 children up to the point of the leaf nodes. Where on this tree on the right, each tree only has one child. Now let me remind you, that thing on the right, even though it looks like a linked list, is a tree. It has nodes that have at most one parent, or that have at most one parent, and between 0 and 2 children. In this case, they only have right children. But that's still a tree. It's still totally allowed. And so you can get wildly different trees of the same height. On this slide, we have some numbers here that are sometimes useful to kind of just have in the back of your head when you're thinking about how you reason about tree heights, is between like kind of these two extremes. A completely full tree of height h and a tree that's as empty as possible that still has height h. And so you can usually think about, well, what's the maximum number of leaf nodes that you might encounter? What's the maximum number of nodes in total? So here we have the maximum number of leaf nodes in this full tree here. That's going to be 2 to the h. And it kind of goes back a little bit to something like the tree method, where we're thinking about, oh, if you're doubling each time, it's just going to be like that 2 to the I, where I is, in our context, the height of the tree h. Now, we also might want to be curious about, well, what's the just total number of nodes in total? In this case, it's going to end up, for this kind of case of a completely full tree of height h, we're going to say that there's going to be 2 to the h plus 1 minus 1 nodes in total. Now, how could you figure that out without knowing that off the top of your head? Yes, you could use that finite geometric series to add up all the levels, how many nodes are at the ith level. So it's kind of a lot like the tree method, the math in order to do this stuff. So that's like the most nodes possible. But there's also a case with this least nodes possible, where we kind of have this tree that kind of just goes in one direction. In this context, the minimum number of leaves is just going to be 1, because there's only one node in this tree that has no children. And then the maximum number of nodes in the tree will end up being h plus 1. And the reason is, we said here we're constraining our tree to be size h. And if it's height h. If it's height h, that means there's 3 edges connecting these nodes from root to leaf. And edges have to have nodes on both sides. So if there's 3 kind of separators here, there needs to be 4 nodes connecting them. That's why the minimum number of nodes here is h plus 1. So useful things to just kind of remember how these trees can vary in terms of the number of nodes in them, even if they have the same height. And that's going to be actually a really crucial point we'll come back to, that the height of this tree is going to be the thing that really matters. So, I can't move forward. Now I can move forward. There we go. So one other thing that we introduced in 143 is this notion of a binary search tree. And the reason we want to include this binary search tree is it allows us to speed up searching for values. So now when you want to find a value inside a tree, the binary search tree property is one that lets you kind of eliminate nodes that you need to search for through each time. So I'll get to reminding us what the binary search tree property is. But one thing I want to talk about first is what we've done when we introduce this concept of adding structure to the tree, like it has to be in some sorted-ish order to help us find things. That's adding an invariant. Invariants are rules to your data structure or your algorithm that must be true, and they usually are there to simplify things. So when you implement an operation on your data structure, you know that that invariant is going to be true at the beginning, because invariants are things you assume, and you have to do everything in your power to make sure that they're going to be true after your method's call. And usually when you're programming things, if you violate one of your invariants, it's usually one of a very common source of bugs, because you just maybe accidentally violated an invariant you thought would be true. And so it's really helpful if you actually try to codify what your invariants are, so you can easily check them in your code just as a sanity check to make sure everything's working. So the binary search tree invariant is one such that for every node with some value k, the left subtree has only keys smaller than k, and the right subtree only has keys greater than k. And this invariant is adding a rule on which trees are valid. Binary search trees are a subset of binary trees. There are a lot of binary trees that are not binary search trees. So this invariant, though, lets you speed up your search, because now, say you're searching for some key, you don't have to search through the whole tree. you could take advantage of the fact that you know that there's this structure here. So, So say, for example, you're looking for the key 14. You would start, the way this algorithm works is you'd start at the top, and then you say, well, I'm looking for 14. Is 14 bigger or less than 9? It's bigger, so it's going to be in the right subtree. There is no need to check the left subtree at all, because I know 14 is bigger than 9. And then you could just keep doing this over and over again. Well, is 14 bigger than 10? It is, so go to the right. Is 14 bigger than 30? No, go to the left. Hey, we found a 14. We would comport. It's in this tree. So this invariant lets us kind of speed up our search. So we'll talk about how to quantify that in a second. But one thing that's really important to highlight about this is that this BST ordering property, binary search tree ordering property, applies recursively. It has to apply to all children in the left tree and all children in the right tree. And not that like every subtree needs to be its own binary search tree, but kind of the data in the nodes earlier on have more and more constraints for the data lower on. So for example, the binary search tree property for this tree says that since 9 is that root node at the top, all of the nodes to the left have to be less than 9, and all the nodes to the right have to be greater than 9. Okay, I kind of remember that from 143, binary search trees. Now, but this property has to apply recursively down. So if you consider down here, this, If you consider down here, this subtree, well, all of these nodes have to have data less than 9, but then also this needs to be its own binary search tree. So since this subtree is rooted by 3, all of the things to its left must be less than 3, and all of the things to its right must be greater than 3. But those constraints are also subject to the earlier constraints. So it's actually not just anything less than 3 or anything greater than 3. It has to be all things less than 3 and less than 9 on the left, and things greater than 3 and less than 9 on the right. And so usually that's really tricky, that like the earlier decisions kind of make their way down that tree. So that's a really important thing that we want to stress. Now, one other thing I want to kind of quickly mention, because it's going to get a little confusing in kind of the rest of this lecture. We're going to be talking about these trees in the context of a map ADT, so something that maps keys to values. And so you might be wondering, well, how can I do this binary search tree property if I have both keys and values I need to look at? So usually what we'll end up doing is we'll just add a value field to our node, but we really only care about the key for all properties of searching, ordering, etc. When we're thinking about how do we order this tree, we're going to order it by the keys. We're basically going to ignore the values for all purposes other than, oh, you called get here and we found the node with the right key, now it's time to return that value. For all other parts, the value part of the map is just not going to be important. There's going to be extra data floating around. So keys are going to be the important thing here in this context. And so I kind of quickly mentioned here that this binary search tree property helps us search through data. So if you have these two trees with the same number of nodes, and you're trying to search for the key 5, well, without the binary search tree invariant, when the data can be in any order, you're gonna have to search the whole tree for that value. But with the binary search tree invariant, you can sort of eliminate half the tree each time, and you can speed up your search because you kind of have a good idea of where the data is. So in our next video, we're going to talk about how we quantify this, how we can actually use our asymptotic analysis tools to kind of look at this stuff.